Equivalent fractions. The way I sort of teach it is I think about a pizza for a lot of students, and when I start teaching you how to add, subtract fractions, think of a pizza will make more sense, especially for 3B, will make more sense of why picturing as a pizza makes it easier to understand. But let's start off here. That's one whole pizza that you can have. But you can cut a pizza into many different pieces. Out of curiosity, anyone know when you go buy a pizza from Domino's, how many pieces do they cut it up into? Does anyone know? 8. Okay, so generally they go for 8. And to do 8, they'll likely go 1, 2, 3, 4. Okay, so that gives you then 1, 2, 3, 4 on one side, and then 5, 6, 7, 8. So there'll be 8 pizzas. Okay, so that's usually what you get when you go to a pizza. Sometimes I've seen Pizza Hut do it 6 pieces instead. So you get your, I don't even know how they do it. How would they do it? They'll do 1, 2, is it 3? Yeah, like that. So that's your 1, 2, 3. So you get your 6 pieces there. But usually it's 8. Now, because there are different ways of cutting it, that also means that each person, when you pick up a piece, each piece will be different in terms of its size. So here, I've done 1 cut. So you can see here, I'm doing 1 cut of the whole pizza. This is one portion that someone can pick up. So they can pick up half of a pizza, 1 out of the 2 pieces that are available. Okay, because if I did 1 cut, there are 2 pieces available. And then when you pick one, you get 1 piece out of 2. That's a really big piece. Okay. Versus over here, I can do 2 cuts. So we can see 1, 2. How many pieces of pizza have I made with 2 cuts? Can I please have Hamza? How many pieces of pizza can you see? How many pieces of pizza? So if I did 2 cuts, I'll do it again. This is your 1 hole. I cut it once, cut it twice. How many pieces of pizza can you see? 4. There's 1 piece over here, 2, 3, 4. So when you say that, each one, this piece over here is equivalent to 1 out of the 4. But see, if I ate 2 of them, so if I ate this one and ate this one, to keep the same shape as I have over there, I need to eat 2 of those quarter pieces to make 1/2. Then, interestingly enough, as you increase the number of cuts, so if I do 3 cuts now, 1, 2, 3, we can see now there are 6 pieces. 1, 2, 3, 4, 5, 6. How many do I have to eat of these 6 pieces? How many do I have to eat to make half? How many do I have to eat? 3, logically, because here was 1, 2, 3. I need to eat 3 to make half. So visually, it makes sense that the more I cut, the smaller the pieces are, but that means you have to eat more of those pizzas, right? So here we've got 1, 2, 3, 4, but that means it's out of 8. There are 4 out of 8, and then same thing here. This is now 5 out of 10. One of the things that you learnt in primary school for equivalent fractions, the reason why all of this is equal is you can see that they're all the same amount of pizza. You either get 1 big piece, or you get 2 smaller pieces, or you get 3 even smaller pieces, or you get 4 even smaller pieces, right? So because of that, what we can see is all of them are equivalent, but they are different. When you write 10, 8, 6, 4, and 2 as your denominator, they are not the same type of pizza. Each one is different. So one is this shape, the other one is this shape, the other one is like that shape. Each one is a different piece, even though collectively it is the same. So what they then did is they said, usually in primary school, this is how they teach you. They say, to go from 2 to 4, what do I have to multiply? 2. So to go from 2 to 4, I have to times 2. But whatever you do to the bottom, you do. And this is my question. Why?
So you can make it the same.
Because you want to make this the same. But there's even more of a logical, mathematical reasoning to this. Okay? Here's the reasoning. Half, right? That's just 1 piece. That's 1 type of fraction. True? So remember how I said each piece is different? This is a half a piece. This is a quarter of a piece. This is a third. They're all different pieces. How can I change this fraction by saying, oh, whatever you do to the bottom, you do to the top. You times bottom by 2, you times the top by 2. But you know what's interesting? You can't do this. See, we say we can do times, and you said, well, it keeps it the same. Then why can't I do 2 plus 2 and then 1 plus 2? Why doesn't that work? See what I mean? So the one thing, you memorized what they taught you in primary school, but no one really asked you, why is that true? Why is it that you can't do it when it's add, but you can do it when it's times? Anyone have a clue? It's more of a logical reasoning here. So I'm pushing your understanding. Rather than just teaching you to memorize maths, because that's what most people do, I'm trying to get you to understand. Why is that true? Why is that true? Why is it just times? So here, this is the answer, because most of you would not have seen this in the past. Most teachers don't teach you this way. A half, if I asked you, what's a half times 1? What's half equal to? Still equal to half. So I haven't changed it, have I? I times it by 1, hasn't changed. What is 1 as a fraction?
Everything.
1 is everything, but writing it as a fraction. So this is a whole number. How do you write it as a fraction? 1 over 1. Now, when I times it, 1 times 1 on the top. So when you times fractions, we know top with top, bottom with bottom. 1 times 1 gives you 1. 1 times 2 gives you 2. Still correct. Now the key part is here. You told me that as long as you multiply by 1, it'll always stay the same. But there's a lot of ways of writing 1. You see, 1 divided by 1 is the same thing as saying 1 over 1. 1 divided by 1 is 1. But you could also say 2 divided by 2. What's 2 divided by 2? 1. So who said that it had to be 1 over 1? It could have been 2 over 2. But if it's 2 over 2, what would this fraction be? That's where it's coming from. 2, 4, because you told me before half times 1 is still equal to half, that means 2 over 4 must still be the same as half. This is why timesing by 1 makes sense. That whatever you do to the top, you have to do to the bottom. Why doesn't add work? Well, if you tried it, even if you change this to 1 over 1, one of the first things you know about addition of fractions, they are different pieces. This is a half of a pizza. This is 1 whole of a pizza. You can't then say 1 plus 1 is 2 and then say, well, this is 2 plus 1, that gives you 3, because I don't have thirds. That's not a third of a piece. That's 1 whole of a piece. And that's 1 half a piece. They're very different. If you went up to pizza and opened up a box in Domino's and a box from Pizza Hut, they're different pieces on how they cut it. So you can't just say, oh yeah, the numbers say you can add them and therefore it works. That's not true. So what I want you to understand from this is the reason why you can do top times bottom is because you're really just timesing by 1. That's what you're actually doing. That's why it doesn't change. Adding, subtracting, well, why can't you add them and why do you need the denominators the same is because they are different pieces. Just like these tables and chairs. If I asked you how many tables there are, you would count 1, 2, 3. There are 3 tables there that I'm looking at. But you wouldn't then go 1 and then 2. This is different. This is a chair. A chair is different to a table. You wouldn't say I've got 2 tables. And you wouldn't say I've got 2 chairs. Well, it's the same thing with fractions. You wouldn't say I've got 2 of the same pizzas because they're different. Just like tables and chairs. So a half is a different to a 1. Or it's different to a third. And it's also different to a quarter. Just like chairs are different to tables, and tables are different to lights, and lights are different to curtains. When you count things, you look for the same things. That's why when you're adding fractions, you need to make sure they are the same type of fractions. Does that make a bit more sense? Okay, so that's on a theoretical base. If what I said confused you, you can scrap it all and you can just memorize maths. That's pretty much how most people learn maths anyway, which I think that's why people make mistakes when they get up to year 9 and 10, because they don't get the logical part to it. Okay? So I'm going to delete this bit now just so that you have an understanding. So now, today's lesson, if you didn't understand the theory of why fractions work the way they do, then this is what you're going to memorize now. Fill in these spaces here for me. Note each fraction with a different, fill it in, denominator. Denominator means the bottom number. That's what denominator means. Is a different type of fraction. That's going to be key so that when you learn to add, subtract, you need to understand that each denominator, every time you have a different number, it is a different type of fraction. It's like tables and chairs. And not every table is the same too. This is a table, this is a table, this is a teacher's desk, and that's your common student's desk. They're different. If I asked you how many teachers' desks there are in this room, you'd say there's one. If I asked you how many tables there are, then you would count tables in general. Okay? Here we go. So what's today's goals? Today is using that knowledge that we now understand. Equivalent fractions, 4/5. You can change this to any fraction you want because you know that 4/5 times 1 is always by itself, and then 1 is the same thing as writing 1 over 1. So as long as you times it by whatever number it is on the top, the number on the bottom must be the same to make sure it's still 1, and it works. So this is where you do a bit of logical thinking. You say, well, 5 times what to get that 50? 10. So this number here has to be 10 on the bottom. But then to make it 1, because we need it to times 1, that means the top has to also be 10. Because 10 divided by 10 is still 1. So 4/5 times 1 still equals 4/5. That's why when you times it, 4 times 10 gives you 40 on the top. 5 times 10 gives you 50 on the bottom, which is what you wanted. You wanted that 50. That means the top has to be 40. This is called equivalent fractions. Okay, and equivalent fractions goes with that basic understanding that you're really just timesing by 1. This here is always 1. That's the goal. Okay, the goal is to get the 1. 10 divided by 10 is always 1. Yeah? So whatever you do to the bottom, so that's why they say if you times 10 to the bottom, you times 10 to the top. That's why they teach you that way. Okay? So using that same understanding, let's do it the other way now. 200. I needed to make it 50. If you can times, remember times is the same as division. Division is just the reverse, is just the reciprocal of times. So here, 200, instead of saying times, we could also think of it as division. 200 divide what will give you 50? 4. And then whatever you do to the bottom, you must do to the top. And 80 divided by 4 gives you 20. This is called equivalent fractions. Okay, and for those who are curious as to why divide is the same as times, well, 200 divided by 4 is that, but that is also the same thing as writing 200 times 1 over 4. That's why. It's the reciprocal. Okay, so instead of writing 4 over 1, when you divide, it's actually the same as saying times 1 over 4. That's why that works. Okay, so you could have said, here you could have said times a quarter, and you could have said times a quarter, and it would have been the same answer. Okay? But division makes it easier for you guys to understand. Okay, so that's why I wrote division. So divide 4, divide 4. All right, team, let's go to the next question. Let's see if you can fill this in. I'm going to pause the video. You got